All right, sections 5.3 and 5.4, growth and decay, exponential functions, and E. Nothing in this lesson is new, so we're not going to spend a whole lot of time on these two lessons. All right, exponential functions are in the form ab to the x power, right? Our unknown is our exponent instead of being our base. A is known as our initial value. That's also our y-intercept. And that occurs when x is equal to 0. So that's a very important point when we're talking about the graph of these functions. B is our growth factor. If B is bigger than 1, it's exponential growth. If it's between 0 and 1, it's exponential decay. So we model functions using, again, something that is familiar to you. A sub 0 is our initial value. That occurs when our time is equal to 0. R is our rate, T is our amount of time. So if we're representing an increase in value, we take 1 plus the rate. If it's a decrease in value, it's 1 minus the rate. And our rate is always expressed as a decimal. Okay, so applying these in interest functions, these would be annual interest. This is compound interest. And these are what we studied. N is equal to 4 for quarterly, 12 for monthly, 365 for daily. Okay, you guys spent a lot of time with those. And the PERT formula is when we earn when it's compounded continuously. Okay, so that's our key word there. On the compound interest, notice the number of times that we earn interest, that has to be included in our exponent as well. Okay, f is an exponential function where f of 0 is equal to 3 and f of 2 is equal to 12. Find f of x. So it's an exponential function, so we know its parent function is ab to the x. If f of 0 is 3, that's the point 0, 3. That's my initial value, so I automatically know that a is equal to 3. Now to find the value of b, our growth factor, that's where we plug in our other point. Okay, so when f of x is 12, x is equal to 2, dividing by 3 on both sides, and now I'll take the square root, and I get 2 is equal to b. Now, I'm going to keep b positive and not negative because I'm representing exponential growth here. If I look at my y values are getting bigger. I'm not going to have b equal to negative 2 because if it were negative 2, then it would be a reflection of the graph. So we'll just keep b positive. So f of x is equal to a times b to the x power. We just spent a ton of time on exponent rules. The x is only an exponent to the base 2. Okay, 3 our initial value. According to our order of operations, that would come next. All right, f of negative 2, replacing now my exponent with negative 2. Back to our exponent rules. F of negative 2 would equal 3/4. Okay, now these 2 points fit an exponential function. But now we don't have the initial value. So what are we going to do with this information? We're going to plug it into our function. So I'm going to create 2 equations. F of x equals ab to the x power. That's plugging in the point 4, 5/4. And then f of x equals ab to the second power. That's plugging in the point 2, 5. Okay, our next step, we're going to divide these 2 equations. Okay, piece by piece. So 5/4 divided by 5 is the same as multiplying by a fifth. So here I would get 1/4 equals, dividing these, the a's cancel out. Dividing like bases, I subtract exponents. So I get 1/4 is equal to b squared. Taking the square root of both sides and just keeping the positive answer, now I have my value of b. Okay, so f of x equals a times 1/2 to the x power. Now just looking at that, if b is equal to a half, this would represent exponential decay. And that makes sense because as x is increasing, my y values are getting smaller. So now pick one point, does not matter which one you choose, to be able to solve for a. So I'm going to get 1/2 to the second power. 5 equals a times 1/4, squaring both the top and bottom. So 20 would be my initial value. F of x equals a times b to the x power. There's my exponential function. Okay, using the models in a certain city, the value of a house is increasing at an annual rate. Okay, and then just to look at 4, in 4 we're decreasing at an annual rate. So we're going to be using this model. A equals P, 1 plus the rate to the t power. Okay, I just looked back at my notes, I fixed that up. A is equal to P times 1 plus R to the t power. So if our rate is 3.5%, as a decimal, that would be 0.035. Now for my equation, I have to add 1 to that. So then my amount after 4 years, so the value of the house after 4 years, the initial value of the house is $200,000, 1.035, and I raise that to the 4th power. Use a calculator, find that answer for me. So now to set up number 4, if I'm decreasing, my rate as a decimal is 0.082. So when I take 1 minus that rate, I get 0.918. And that makes sense. If this is what I'm plugging in, then it's going to be exponential decay. So the value of the home after 4 years, home was originally worth $200,000 times 0.918 to the 4 power. So evaluate both of those, and you definitely need a calculator for that. Okay, if you double your money in 15 years, what would your annual interest rate be? So this rule of 72, if a quantity is growing R% per year, then the doubling time is approximately 72 divided by R, either in years or months. So we're dealing with years here. So the time it takes to double, using the rule of 72, is 72 divided by R. Well, you're told you double your money in 15 years. So solving this equation for R, we get R is equal to 4.8%. And this is a very useful tool where you don't have to worry about setting up an exponential equation and solving for R. Okay, the table shows the number of bacteria in a nutrient solution at various times. The bacteria population is growing exponentially. So hopefully you're seeing exponentially means we have some common multiplier, okay? How did the population change from 3 hours to 9 hours? So I can take the values of my population and simply divide them. So when I divide this, the population got 3 times larger from 3 to 9 hours. That does not mean that our growth factor is 3, okay? Find an equation for P of T. So this is where I have to pick 2 points and plug them in. I'm going to pick this one, and I'll pick this one, just because it asked it for an A. But you could have used any combination of the 2 of them. Population is A times B to the 9th power. Okay, so I'm just replacing my Y and my X with the values from the table. Population of 260 after 3 hours. Okay, now we divide the equations piece by piece. So we already said 780 divided by 260 would give us 3. The A's cancel out when we divide. Subtracting exponents, we get 3 is equal to B to the 6th power. So how do we solve for B? We take the 6th root of both sides. Now, from our study of exponents, in your calculator, you could also raise 3 to the 1/6 power. Okay, just be careful, parentheses if you need them. All right, so this B comes out pretty well to 1.2. I think there's like 2 or 3 zeros after the 2, so that's what we'll leave it as. Now we got to find A. So I pick one of the points, doesn't matter which one. I'll take the 9, 780 equals A times 1.2 to the 9th power. Okay, let your calculator do all the work. Okay, do not approximate this as a decimal. Into your calculator, plug in 780 divided by 1.2 to the 9th power. To 3 decimal places, I got 151.169. So my equation to represent my population would be my initial population, 151.169. My growth factor is 1.2 raised to the t power. Okay, it verifies that it's exponential growth because that value of b is bigger than 1. Answer this for me. What will the population be after 1 day? Just be aware of your units, okay? How is your time measured? Answer that question for yourself before you just go plug in values in. All right, the value of a $24,000 machine decreases 9% each year. What will the machine be worth in 3 years? Okay, so here we have our annual decrease. So my rate as a decimal is 0.09. So my base, when I subtract 0.09, now I get 0.91 for my equation. Makes sense that it's exponential decay. So the amount after 3 years, initial value is 24,000, and then 0.91 to the 3. Okay, grab your calculators, evaluate that for us. Now this one, in how many years will the value of the machine be about half its value from when it was new? Now we're solving for our unit of time. In how many years? So t is our exponent. So I'm going to plug in half its value. So if it's worth $24,000 now, half of its value would be $12,000. There's my t. Dividing both sides by 24,000, that's where my half comes from. And something we'll talk about in class and actually use on the next slide, it does not matter what the initial value is. If it's half its value, then that's where my 1/2 comes from. Okay, so I'm giving you lots to do with your homework tonight. Use guess and check and find a value for t. So I'm going to know between what 2 years will this be true? Okay, do a little guessing and checking with your calculator because this is exactly what we start looking at when we look at logarithms and natural log next lessons. All right, and then last one, you're going to do this as well. Which plan yields the most interest? Okay, it does not matter what the initial value is. You can pick whatever number you want. I would suggest just simply keeping it easy. Pick the number 1. Okay, so for each of these, we're going to let p equal 1. Go back to what these relationships are in slide 3. So go back to slide 3. And each plan gives you a different amount of information to plug into one of those equations. Okay, so please make sure you have all of that done for next class. And then answer. Use slide 3 to answer the question. All right, that'll do it.